to another episode. So today we're going to be continuing our proof of this identity, which e to the I theta is equal to cosine of theta plus I times sine of theta. So last time we proved that e to the x can be written as 1 plus x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed and then plus 1 over n factorial x to the nth power as n goes on to infinity. But now, if we want to finish this proof, then we have to find the Taylor series of cosine and specifically sine of theta, so that we can let the Taylor expansion of both sides match up, and therefore going to be a conclusion. So now let's start. Well, let me erase this. So what is cosine theta? Well, the general idea is that if we can find the Taylor series of cosine theta, then this can give us a clue of sine of theta. So let's start with cosine theta. Something special of cosine of theta is that if we take foreign plus 2 derivative to cosine of theta, then this will be negative cosine of theta when n is a positive integer, or just an integer in general, but have to be greater than 0, greater or equal to 0. But if we take d to the 4n over dx 4n, which this basically means you are taking 4n's derivative, then cosine of theta is going to be equal to cosine of x. Sorry, I should write it as x. So why is that? Well, this is because if we take the derivative of cosine of x, then take derivative, then you go to negative sine of x, and then take derivative, then you get cosine of x, negative cosine of x. So you can see it's basically cycling through two derivatives, which proves this claim right over here, right? So now, how do we generalize something about the thing we just discovered? Well, we proceed by generating a function. So let's say that if cosine of x can be written as a0 plus a1 x plus a base 2 x squared plus dot dot dot. So this will be more convenient once we find some relationships between different terms. Then we only need to be caring about the second derivatives, because the first derivative will not really give us anything. So second derivative dx d squared over dx squared cosine of x, that is going to be negative cosine of x, but we have to express it in terms of this function right over here. So this, we can see that the first two terms basically cancels out, because there are zeros. So this will remain as 2a base 2. Notice that here I'm just keep doing the power rule over here. So a base 3 x cubed, you take 3, you take 2, then you're going to have 3 times 2 a base 3 x squared, no, times x, and then plus 4 times 3 times a base 4 x squared. So you can see, you basically see the pattern, but then we have to make this be negative cosine of x. Then if you take first derivative, then doing the same thing, we're going to be getting 24a base 4, and then plus, well, next one becomes 5 times 4. 5 times 4 over here, right? 5 times 4, and then you have to times 3, and then times 2. So this will give us 120a base 5. And then use the same logic, you get 360 baby 6. Notice that we can see that we can find some relationships. Since they are both constants, then they must be equal to each other, but this must be negative. So we see the relationship of a0 is equal to negative 2a base 2 is equal to 24a is 4. And then, well, what about a1? a1 is equal to negative 6a base 3, which is equal to 120a base 5. And over here, then a3, then a2, a base 2 is equal to 4 times 3, a base 4, which is 12, and is equal to 360. Here should be negative a base 6. So now you can see that it basically makes a generalization, and this is essentially what we're trying to see, because we see that a base 2n is equal to negative 1 to the nth power times a base 2n is equal to negative 1 to the nth power, and then multiply by x to the 2n over 2n factorial, but we don't really have it, so 2n times a0 over 2n factorial, which this is a generalization, and a1 and a base 2n plus 1 we can also make one, but something really important that we have to notice is that cosine of 0 is equal to 1, and sine of 0, negative sine of 0 is equal to 0. Because when you let x equal to 0, then the only constant left over is a base 0. But if we take the derivative of cosine of x, then sine of negative sine of x when x is equal to 0, then by the unit circle, then sine of 0 is equal to 0. And negative 0 is still equal to 0, so it's meaningless. So what does this mean is that we can just neglect all the odd terms. And now we're only left with even terms. But even terms, we know that a0 must be equal to 1. So now this formula just takes place that we can find all of the coefficients. So let's start. So basically, according to that formula that we deducted, then cosine of x is basically equal to 1 minus x squared over 2 factorial, then plus x to the 4th over 4 factorial, then minus x to the 6th power over 6 factorial, and plus blah blah. And the generalization is negative 1 to the 2nth power times 2 times x to the 2nth power, and then over 2n factorial when n goes to infinity. Now we don't really have to work about sine of x. Well, why is that? This is because we can see that sine of x, everything is exactly the same. So sine of x, you go to cosine of x when you take the derivative, and then you take derivative again, then you will get negative sine of x. So you can see the derivative, the pattern of derivative is essentially the same, but we're just flipping sine of 0 is equal to 0 and cosine of 0 is equal to 1. So basically you see that d over dx1, well, when sine of x is equal to, when x is equal to 0, you take sine of x the derivative, then it's equal to 1. So basically you're flipping cosine of x and sine of x with their base conditions. So basically with sine of x, we're going to preserve the odd terms and neglect the even terms. So sine of x, well, we already got it, right? So instead, a0 will be equal to 0, and a1 will be equal to 1. So basically, sine of x is just equal to x minus x cubed over 3 factorial, then plus x to the 5th over 5 factorial, and then minus x to the 7 over 7 factorial. And then generally, it will become negative 1 to the nth power. So negative 1 to the nth power times x to the 2n plus 1's power over 2n plus 1 factorial, when n goes to infinity. Thank you for watching. Hope you enjoyed. And in the next video, we will be finally concluding this and proving that e to the pi's power is actually equal to negative 1.